I'm the Director of Knowledge Management for the Open Geospatial Consortium. Thank you very much for this opportunity to brief you on geospatial standards for data science. First, just a brief overview of my background. I joined the OGC as staff about 18 months ago, but before that, I worked for a company, a small to medium-sized software company that does a lot of work for one of the major government ministries. And before that, I worked as a postdoctoral researcher at the University of Nottingham, as well as at Newcastle University. So the talk this afternoon is based on the work that the OGC, or the Open Geospatial Consortium, is doing and how it relates to data science. So hopefully many of you across the room will find that it resonates with various aspects of your work. So an overview of the presentation. I'll start off with a description of some of the data sources that we encounter within the geospatial sciences and engineering, as well as the motivation for interoperability. I'll then move on to describe some of the data encodings and analytics methods that are applied and how standards relate to those methods and encodings. I'll then move on to describe the semantic web and linked data, how it's being applied within the geospatial domain, as well as some of the standardization work that's ongoing around the areas of cloud computing, machine learning, and similar areas. And finally, I'll provide a summary of some of the work that we're doing with regard to technology trends analysis and forecasting. So the Open Geospatial Consortium has a mission to advance the development and use of international standards that promote geospatial interoperability. We do this by providing a international global forum for data providers, solution providers, to discuss some of the issues and requirements that they encounter within their use and application of geospatial data. The OGC itself, as an organization, it's an international consortium, currently with more than 520 member organizations that include government departments, private companies, universities, literally from across the globe. And these organizations collaborate in a consensus process to develop publicly available interface standards that promote geospatial interoperability. The organization was established in 1994, and within the past few decades, more than 100 standards have been developed by the OGC. Some of those standards have also been adopted by some of our alliance partners, for instance, the International Organization for Standardization, or otherwise known as ISO, but also other standards development organizations such as the World Wide Web Consortium. More than 700 products implement OGC standards. And these products are developed by not just commercial organizations, but also nonprofits, universities, and other organizations. Our membership, as well as the products that implement OGC standards, cover basically more than 45 countries. And what we've done is to organize the consortium into working groups that focus on domains, working groups that focus on specifications, but we've also set up forums, regional forums. So there's a UK and Ireland forum, there's a Europe forum, there's a North America forum, and for other regions as well. So I thought we'd first of all explore why geospatial information is relevant, why it's important. There's a quote that's usually mentioned from, I think it's 1987, from a Research Journal article, which states that more than 80% of information needs of policy and decision makers relate to geography. That quote is quite important because it highlights the impact that geospatial information or geography in its broader sense, how it impacts everyday lives. Another quote from a book by Longley and his colleagues states that almost everything that happens somewhere. So if you think of an event, chances are that event has some form of location or geographic location. It happens somewhere. Now, these codes effectively highlight the key role that geography plays in various aspects of society, and therefore the need to find ways of bringing all that insight or extracting that insight become even greater when you consider, or at least when you try to extract knowledge and from all the data that is out there. To address the geospatial interoperability challenge, the geospatial interoperability challenge is that need to try and bring together various types of geospatial data in order to inform decision making and to support science and other areas of knowledge. To address the geospatial interoperability challenge, the OGC members have developed standards that have been implemented by thousands of services. So I mentioned 700 products. Those more than 700 products have been deployed across the globe, creating thousands of services. Those services publish literally millions of data sets. Those standards make it possible to exchange geographic information and other types of geospatial information, to exchange it with minimal loss of content. Some of the more popular standards include the Web Map Service, or WMS, the Web Feature Service, and the Web Coverage Service. The WMS provides a way of publishing and requesting rendered digital maps. So a client application can basically say, we'd like this type of data from those databases, and we'd like it rendered using a particular style. So the Web Map Service supports that. The Web Feature Service provides a means of publishing vector feature data, providing fine-grained access not just to features or objects, but also to properties or attributes, for instance. Then there's the Web Coverage Service, which I think for data scientists will be of particular interest. The Web Coverage Service provides a means of publishing multidimensional coverages that can then be integrated into systems that support, for instance, multi-array based analysis. There are also other standards, for instance, KML, better known as the format that better known as the primary format used by Google Earth. Then there's GML, or the Geography Markup Language. GML is the primary format used by the Ordnance Survey's master map product. It's also the primary format recommended by the European Commission's Inspire directive, as well as in other communities as well. A more recent standard is GeoPackage, which provides a way, it standardizes how you store geospatial data in SQLite databases. If you have a mobile phone, it has chances are it has an SQLite database inside it. Definitely Apple, iOS, and Android devices tend to have SQLite databases. So GeoPackage provides a standard way of actually encoding that information. I'll skip to NetCDF. NetCDF is used primarily in the space and meteorological communities. It provides a way of storing and accessing multidimensional arrays of data. And the reason why I say it's likely to be of particular interest to the data science community is because I know a lot of work that or at least a lot of research that takes place within data science projects involves multi-dimensional array content as well. So those are some of the standards. But then what is an OGC standard? An OGC standard is a document established through consensus and approved by the OGC membership. Remember, I said the OGC membership currently stands at more than 520 member organizations. An OGC standard, that document provides rules and guidelines aimed at improving or optimizing interoperability within a given context. The standards have been developed by taking into consideration requirements from various communities, but also requirements from the membership itself. But we also ensure that we monitor what happens in the market, technology trends, and use that insight to inform how the standards are actually specified and how they adapt over time. This picture was taken at a technical committee, an OGC technical committee meeting held recently. We hold 4 technical committee meetings, usually in different parts of the world. And usually we have about 200 delegates attending those meetings. And the attendees of these meetings take part in a whole variety of discussions to help formulate those specifications, those OGC standards. This slide shows a larger view of the OGC services architecture. Now, you probably will not see all of the content from the back, so I'll just mention a few. So earlier on I mentioned the web map service, the web feature service, and the web coverage service. There are other standards as well that support either the collection, processing, or dissemination of geospatial data. For instance, the SensorThings API. The SensorThings API provides a RESTful interface as well as a JSON messaging mechanism for publishing data from sensors, but also for accessing those sensors or even tasking those sensors. So consider, for instance, sensors aboard satellites or sensors aboard vessels, or even in situ sensors used to monitor various aspects of the environment and to support Earth observation. There is also a standard called GML-JP2 or GML4 JPEG 2000. And what this standard does is that it provides a standardized way of encoding or describing what coverage data set is and storing that information within a JPEG 2000 image. There are several other standards. I will not go through all of them, so I'd just suggest maybe having a look at some other point in time. Many of those standards are implemented by software products across the globe, not just commercial off-the-shelf software, but also open source software. The products that implement these standards cover a wide variety of programming languages. For instance, with Python, there's a Python library for GDAL. In fact, GDAL itself is built using C++, but it has Python bindings. And this is a library that makes it possible to convert between various formats, some of them being OGC standards. And by virtue of being Python, it makes it possible to pull it into data science applications, for instance, using it alongside TensorFlow and NumPy and others. There's also the GrassGIS, which has a plugin for R. So that makes it possible to integrate it with data science applications that use R. And then another one is, as for Java, there's a library out there called GeoTools. These are all open source libraries. There are also commercial off-the-shelf libraries out there, but I'm just mentioning open source ones for the time being. So with Java, there's a library out there called GeoTools, which supports quite a number of OGC standards. By virtue of being Java, it means that it can be used alongside deep learning for Java or DL4J, another library that is used in quite a number of data science applications. And then finally, there's a library called the Orfeo Toolbox, originally developed by the French Space Agency, which it's built using C and C++, but it offers a machine learning framework that supports neural networks, decision tree classification, and several other algorithms, and focusing squarely on remote sensing imagery. Those are just examples of some of the programming languages and the types of software that support OGC standards, which could be pulled into data science applications. But then where does all this data come from? Well, geospatial data is pretty much everywhere, right? Whether it's from satellites, sensors aboard satellites, many of the satellite missions, whether from NASA, ESA, or from other agencies, many of them collect and publish geospatial data. But there's also the Internet of Things, or the IoT, which many of the devices that are being developed to form part of the IoT have a means of tagging the data that they collect with geospatial location or geolocation. Some of those coordinates might come from GNSS chips, or such as GPS or global navigation satellite systems, but some of them are actually sourced from IP addresses, for instance, or other means as well. All of the data that comes from whether it's IoT or other sources, if it has location, then it has a role to play within geospatial decision making. So within the OGC, what we've done is to develop a suite of standards called the Sensor Web Enablement suite. It includes a number of standards, for instance, the Sensor Observation Service, which provides a way of publishing observations collected by sensors. There's the Sensor Planning Service, which makes it possible to task sensors, for instance, to task a satellite to collect data at a particular location and at a particular time. There are other standards such as Sensor ML, or the Sensor Model Language, which makes it possible to describe a sensor in a way that makes it possible to exchange that information with other applications. And so the Sensor Web Enablement suite of standards describe both the syntax as well as the semantics of a whole variety of aspects relating to sensors, but also the relationships between all those aspects, whether it's the observations, the sensors, the features of interest, the procedures, or even units of measure. Some examples of programs that make use of sensor web enablement standards include the UK's DEFRA Air Quality Program. So the government department, DEFRA, publishes air quality data in near real time. I think it's every hour. And that data is immediately made available through a variety of means, one of which is the Sensor Observation Service. There's also the Australia Water Data Online, which the Australian government uses to publish data from sensors deployed pretty much across the Australian coastline, but also from other waters, Australian waters. Then there's the European Union's Inspire Directive, which is it's a directive to establish a spatial information framework across Europe. For sensor-based data or data collected through sensors, Inspire requires use of sensor observation services. And then in the US, there's the National Oceanic and Atmospheric Administration, or NOAA, which publishes data from its buoy network from across the US coastline. It publishes data using OGC Sensor Web Enablement standards. And then finally, NASA has a Sensor Web program which uses OGC standards. And they use them to publish data from satellite missions, but also data from some of the unmanned aerial vehicles, such as the Global Hawk UAV. And all this data is there for data scientists to leverage, to explore, to apply into the research that you conduct here, but also with colleagues. So the OGC, working alongside the World Wide Web Consortium, the W3C, developed a semantic sensor network ontology, with the idea being to make it easier for geospatial data to be plugged into the linked data cloud and to be integrated into analysis involving linked data. The semantic sensor network ontology describes entities as well as relationships that identify, for instance, sensors, actuators, samplers, and so on. It provides just just enough semantics to be able to apply these sensors to a variety of applications. It's also aligned with the OGC and ISO's observations and measurements standards. So this is a standard that originated within the OGC and has been adopted by ISO. What it does is it provides a way of describing observations as well as measurements, providing a common way of describing units of measure, for instance. Joint OGC and W3C work has also led to development of the time ontology and OWL specification, which provides a standard way of describing temporal relations, as well as temporal reference systems, including clocks and calendars, type positions and durations. So it's not just the spatial side that is of interest to the geospatial community, but it's also the temporal aspects. And all of that information immediately becomes available for exploitation within data science applications. If I relate it, for instance, to recurrent neural networks, which effectively one of the key things about RNNs, as they are referred to, is the fact that they are time aware. You can immediately see how a specification such as the time ontology and OWL specification, how it could potentially be leveraged by deep learning systems and RNNs specifically. I mentioned earlier on that some of the encodings that we work with relate to coverages. So the coverage data structure provides a way of encoding information about continuously varying phenomena or phenomena that varies over space. Some of the more obvious examples include raster images, but you also get coverages that are built from spatial functions with interpolation between different interpolation at a particular point, returning a value that's been calculated as a result of that function. So the OGC has developed coverage specifications, most notably the web coverage service standard, but also the web coverage processing standard. And those are designed to support coverages. And coverages are particularly relevant because they are, if at a low level, they are arrays. So gridded arrays, which make them well suited for analysis within, with applications or libraries such as NumPy and, used in a number of data science solutions. But coverages are particularly, within day-to-day, day-to-day society, coverages are particularly relevant in metrology, where they are used to support climate science and also to help encode and effectively determine weather forecasts. But we've also seen a shift towards, a significant shift towards data cubes. Multidimensional arrays of coverages that in many cases consider both space and time. And there are a number of federations that have been established in different, with organizations from different parts of the world, where these organizations pull together data from their own data cubes and overlay those data sets in order to support Earth observation and climate science. Some of those federations are at national level. Others are, between academic and academic institutions and research institutions in a broader sense. But all of these are an area that the geospatial standards community is particularly interested in, and we've seen quite a lot of application of those types of data structures concept within geospatial data science as a broader sense. The Earth Science Data Analytics community, there we have been doing quite a lot of work that involves many of the data sets and standards that I've shown here this afternoon. And I've got here a description of how the ESIP community, which is mainly based in North America, how they describe earth science data analytics. And some of this you'll probably see that is quite related to the work that you do here at the Alan Turing Institute and elsewhere. But that definition is that earth science data analytics is the process of examining, preparing, reducing, and analyzing large amounts of spatial, temporal, or spectral data encompassing a variety of data types to uncover patterns, correlations, and other information to better understand the Earth. You can immediately see the overlap and the intersection with data science and the type of research that that we do in this data science community. So many of the techniques that are being explored in earth science data analytics could potentially be leveraged, either by the Alan Turing Institute or by other communities within the broader data science community. Historically, one of the challenges when working with multidimensional arrays was how to overlay them and how to effectively position them to some location on Earth. So a concept called Discrete Global Grid Systems was established a number of years ago to provide a spatial reference system that uses a hierarchical tessellation of cells to partition the planet and address any aspect of the planet. DGGS in particular, there are specific properties that make them DGGS, both with regard to cell structure and geo-encoding, but also the quantization strategy and some of the other aspects that influence the ability to form part of analysis. This slide shows an example DGGS. What hopefully you can see here is that the DGGS in this case is formed of hexagonal cells. Hexagonal cells at different tiers or different levels. And as you drill down into the DGGS, you get finer grained cells. And each one of those cells can be uniquely identified and information retrieved from it. So the OGC developed a standard for discrete global grid systems, which effectively standardizes how to describe them. An information model that covers pretty much all aspects, but also supports different types of cell structures, cell shapes, supporting squares, triangles, hexagons, and other shapes. It also provides a way of uniquely identifying the cells, making it possible to efficiently retrieve information from a cell, regardless of what level that cell happens to be. And by virtue of its very nature, DGGS has found quite an active, should I say, user community at the intersection of geospatial analysis and statistics. And not just local statistics, but statistics right across the board, so even at a global sense. So we've found that DGGS provide a bridge pretty much between geospatial and socio-economic research. In terms of transportation data, a standard called the Moving Features Standard has been developed, which describes how things such as ground-moving vehicles, pedestrians, airplanes, ships, other types of moving objects, how they can be described or encoded in geospatial information. The Moving Features Standard describes, for instance, operations between a trajectory object and a geometry object, describing operations that can be performed on those trajectories, but as well as operations that can be performed between the trajectories and the geometry objects. Remember that within the geospatial context, geometry is actually an abstraction of a real-world feature, whether it's a point, a line, or a polygon. The Moving Features Standard also standardizes operations between multiple trajectory objects, taking into consideration both space and time. So over recent years, what we've seen within the geospatial community is increased use of cloud computing environments So with the amount of data that's generated, you wouldn't be surprised to find that, the ability to handle, petabytes of data and apply them within, your data science research or within other research, that ability is always at the forefront of everybody's mind when we design some of these specifications. So we've seen increased use of cloud computing environments to support the methods, processes, and algorithms that are used by data scientists to extract knowledge and insights from a whole variety of data sets, whether or not they are structured or they're unstructured. And some of the reasons why cloud computing environments have become of particular interest is because of the ability to handle large data sets, so petabytes of data, but also the ability to scale up on demand and scale up with substantial elasticity. And with many of the environments that are out there, they now support a whole variety of programming languages. They have SDKs, for instance, for Python, R, and other languages. So many OGC, or let me say, some of the OGC members have focused on how to make it easier for application developers as well as application consumers to leverage these cloud computing environments. Most notably are the space agencies, so NASA, ESA, and others. They have invested in quite a number of innovation activities to help develop standards that will support the exploitation of geospatial standards within cloud computing environments. And these activities look at how new applications can be dynamically registered within cloud computing environments. They look at how some of the techniques that are out there could minimize the burden on developers or minimize the effort required on developers to enable them to make use of those environments. But they also explore various deployment models, cloud deployment models, whether private, public, or hybrids of the two. And we've also had some recent work done on how to support dynamic scaling of cloud environments. In some cases, not just working within a single environment, but scaling to to pull in resources from other environments. If I give you an example, for instance, some of our work has been with the European Space Agency, and they've been looking at how application developers can make use of both their own private cloud environments, but also how they can leverage public clouds in order to support some of the work that they do. And finally, some of the work, standardization work, has been looking at interoperability between clouds and how open standards can facilitate that. Some of the standards that have been explored include the web processing service, which provides an HTTP interface to a service that wraps analytical capabilities or processing. And then there's the web feature service, which I mentioned earlier on, which provides a way of publishing feature or feature property level data. And then there's the web coverage service, which provides a way of publishing multidimensional coverages as well. I'll highlight the transactional web processing service, or the WPS. This is a concept that has, over the past year, it has formed or helped to formulate quite a lot of the strategy for supporting clouds. So historically, service environments have relied on data being submitted to a service. So a client application would provide data that would be sent to a service provider, where that data would be analyzed and processed. You can imagine how that would be a problem for large data providers such as space agencies, who literally have got petabytes of data, which is always increasing. So the transactional web processing service it addresses that challenge by making it possible for applications to move closer to the data. So making it possible for scientists to take their algorithms and deploy them within an infrastructure that also hosts the data. So that takes away some of the challenges of actually needing to move data around. Now, with many of the, with some of the work that we've been doing within the standardization community, we've been looking at how to apply artificial intelligence and the various levels or various aspects of AI, for instance, machine learning and deep learning techniques, how to apply them within an environment or within various environments that take in geospatial data, take in services of various kinds, and also use cases, and use all of that to design and develop solutions that address real-world needs. The standardization work in this area, as you'd expect, is at an early stage, but it's extremely exciting. This slide shows work that we recently completed as part of the testbed series of initiatives within the OGC. This particular testbed is called testbed 14. It's the 14th one. It's an annual testbed, so that shows you just how long the testbed series has been running. So the participants of the testbed built an architecture that included a web processing service that provided an API around a number of machine learning libraries. They also deployed various web services such as web coverage services to actually supply the data that was then processed and analyzed using the machine learning algorithms that had been wrapped up in the web processing service. But they also introduced a number of components that have not necessarily been explored that much within the wider IT world, and that includes control vocabulary managers as well as knowledge bases. So they introduced some of those concepts and actually applied them within this machine learning environment. This slide shows some sample output. In this case, the machine learning based classification process was implemented around Apache Spark or around the mlib library offered by Apache Spark. On the left-hand side is on that one, that's the input image, and then on the right-hand side, on this side, is that's the actual image post-classification. That same architecture, they were able to apply it to other libraries. So this screenshot shows, this slide shows output generated using PyTorch, which is a Python library for machine learning applications. On the left-hand side is one of the intermediate, left-hand side, that side, is one of the intermediate images that were pushed into the process, and then this image, this side, is the resulting output. So you can see there an example of how machine learning was applied within this context. I should point out that testbeds typically have about 40 participating organizations. Some of them commercial organizations, many of them are research institutes, universities, but also government departments. Now, in terms of how that information, how those maps are communicated outwards, there are a number of standards that have been developed within the OGC to support the publication of visualizations, whether those visualizations are maps or they are 3D models. The web map service, which I mentioned earlier on, provides an HTTP interface for publishing 2D visualizations, 2D with the option of including time. So in some cases, they're enabled to include temporal aspects as well. But it also supports the styled layer descriptor standard, which makes it possible to specify how a map should be rendered. And all of this is done dynamically, or at least can be done dynamically. There's the CTGML standard, which provides a syntax and encoding for 3D visualizations. The screenshot you see at the bottom here is from a program by the Singapore Land Authority. And models such as these have been developed and published on the web, supporting CTGML or City Geography Markup Language. And they've been applied to a whole suite of domains, from transportation to retail site analysis, smart cities, telecommunications, for instance, 5G, and so many other several uses. To support the development of all these standards and to explore how they can be applied in areas and fields such as data science and others, the OGC has an innovation program that runs testbeds, pilots, plugfests, hackathons, research projects, and interoperability experiments. The testbed activity is pretty much our largest activity. It's an annual activity with about 40 or so participating organizations, and usually about 12 sponsoring organizations. But the pilots and plugfests tend to be smaller initiatives focused on very more smaller set of requirements. This slide shows examples of some of the recent engineering reports. Testbed 14 itself has generated about 21 reports. Testbed 13, I think, generated about 23 engineering reports, and so on and so on. But with this slide, what I'd like you to take away is the variety of topics that are covered by the engineering reports. So, from those that deal with machine learning to those that deal with federated cloud computing environments, others that focus on specific standards such as the transactional web processing service. Not just the testbeds produce engineering reports, but also the interoperability experiments. This example here, that engineering report deals with how to use linked data to support environmental science. And that activity was sponsored by the US Geological Survey, or the USGS. There are several other engineering reports on the OGC website. To support how we organize these initiatives, the OGC runs a technology trends activity, which monitors developments, R&D developments from industry, academia, and government departments. And what we do is to analyze these technological developments and try to identify those that are likely to have an impact on geospatial standards and geospatial technologies in the broader sense. We then filter the list down to identify some of the high priority topics and organize events around those topics. And we tend to invite speakers from both within and also outside of the consortium to explore some of the issues around those topics. The work is published on a GitHub site. It's publicly available. It's feel free to visit the website and provide your thoughts and comment on some of the outputs. And that work, not only does it inform the innovation work, but it also informs how we organize our working groups. I mentioned earlier on that we have about 60 working groups. Half of those are domain working groups that focus on thematic areas. The other half are standards working groups that focus on specific standards. This slide shows some of those that I think might be of interest to the data science community. There's a big data DWG, or big data domain working group. There's a Discrete Global Grid Systems, DWG. You recall I mentioned DGGS and the relation to multidimensional arrays and so on. There's also another DWG which is in the process of being established, which is the Geospatial Artificial Intelligence, DWG. It's the community or the work with the member organizations that have been leading the work to establish this DWG are literally spread across the world. We've got some that take part from Japan, Australia, from the US, from the UK. So it's quite an exciting time really to be involved in all these working groups. There's also the statistics DWG, which was only recently approved, and a formal announcement should be made soon. But this will explore the intersection of geospatial concepts and statistics, or the application of geospatial technologies and standards to the statistics domain. And then at the bottom of the slide are some of the standards working groups. that are most likely to be of interest. So, in conclusion, OGC standards various aspects of data science, from the collection aspects to the processing aspects to the dissemination and analysis aspects as well. In each one of those stages, OGC standards and other geospatial standards can be applied to bring a degree of value to the work that is involved. And in terms of the specific areas that the geospatial standardization community is currently focusing on, some of the key topics of relevance to data science include machine learning, cloud computing, the semantic web, and the broader linked data concepts. All of those areas are currently undergoing standardization. There's a lot of research and development that's ongoing. So it's a good opportunity, really, I think, for the Alan Turing Institute and associated universities to get involved in the standardization process and to help influence the direction of travel for many of those specifications. We maintain an ideas factory. So it's a GitHub site where anyone, not just OGC members, can submit ideas. And these are ideas for anything. It can be ideas for how we organize our events to ideas on the types of research that members would like to see conducted within the OGC. It's a GitHub site, so anyone can. It's a public GitHub site, so anyone can access it and basically enter some ideas. So I'd encourage you to visit the site and share some of your thoughts. And for more information about the OGC and other geospatial standardization activities, I'd encourage you to visit the OGC website and explore the innovation program. We currently have about 105 universities from across the globe that are members of the OGC, but we see a lot of the work that we do being used even beyond that. Basically, I'd encourage you to have a look and find opportunities to get involved. And finally, I'd like to acknowledge the support of George Percival, the OGC's Chief Technology Officer, who helped with the compilation of these slides. Thank you for listening.